Hi, my name is Eric Sean, and this is my EX281 IA application. So today I'll be teaching about heap sort. So heap sort is basically a sorting algorithm which takes advantage of the heap invariant and uses it to sort an array either in ascending or descending order. So a heap is an implementation which can be visualized as a binary tree, a complete one. And essentially it's going to either be a max heap or a min heap. And that can be seen by the parents being either greater than the children, or in a min heap the other way around. So a heap sort is twofold. The first step in heap sort is to heapify. So essentially to create a heap invariant. And then the second step is to perform the sorting algorithm. So once you have the heap, you can represent it in an array by mapping every node to an index on the array. So if I have 0, 1, 2, 3, 4, 5 here, I can map it like this in the array. And essentially the idea behind heap sort is that once you have the heap, you can sort it in ascending or descending order. If you want to sort it in ascending order, you want to have a max heap. And if you want to sort it in descending order, you want to make sure you have a min heap. So the way it works is it begins by swapping the last element with the root. And so since we know that the root will always contain the biggest element, we'll be guaranteed that the biggest element will end up right here. And once we've done that, we can seal off this region and end up repeating what I just did with the rest of this array. But first, you need to perform a fix down so that the array, so that the heap invariant is reestablished. So essentially, swapping these two is the same as swapping these two. And then you'd perform a fix down while ignoring the fact that this 9 is in the tree. So you'd probably end up swapping 5 and 4. And the heap invariant is reestablished with the highest element at the 5 spot. So essentially what ends up happening is the biggest element ends up at the top of the array, and once you swap it, it ends up right here. And then you close off this section. So we're taking the biggest elements and closing them in. So eventually we're going to end up with 9, 5, 4, 3, 2, and 1. So this would be our completed array. So the pseudocode for this would look like this. We'd probably have an integer, which is an index, and it would probably be the array's size. Since we're indexing by 0, it's going to be array size minus 1. And then while index is greater than 0, what we would do is we would perform a swap on the root of the array with the smallest element, so with the element at the very back. So that would be array sub ind at the moment. And then we would perform a fix down on the root, which now contains the last element. So just apply the index. And we would decrement ind, so that is essentially closing off the 9 and then closing off the 5, so that the play area for the array decreases with each iteration of the while loop. So the heapify operation has a time complexity of O of n, but that doesn't reflect the time complexity of the overall heap sort, because the whole sorting algorithm is O of n log n. And that is because a fix down operation is log of n time. And since that's within a while loop of O of n, of n, we'll end up with an overall time complexity of O of n log n. So the advantage of this is that, of heap sort, is that we're always sorting in place. So there will never be any extra memory used, unlike other sorting algorithms like merge sort. However, a downside of using heap sort is that you can't make it adaptable, which means that even if the array was completely sorted and you performed heap sort, it would still be O of n log n time because you can't tell whether the array is sorted or not. So suppose this was completely sorted, if we performed heap sort on it, it would end up swapping and fixing down, swapping and fixing down, and it would end up looking exactly the same as before. So that was heap sort. Thank you.